Deconstraining DSLs from...
Okay, thanks for the introduction. This is joint work with my supervisor Tony and Tristan, who I've been asked to say is not here. So, after yesterday's keynote, I feel like I probably should have embedded this talk in a more general purpose talk, but so I'm afraid there's going to be some duplication. So, let's start with some motivation. Heterogeneous parallel programming, it's, well, as we saw yesterday, it's a really good topic, and I know now at least it's on someone else's mind as well as my own. Let's say I've got say two streams of data, X and Y's, and I want to pairwise apply an operation F, say, to produce a new stream, and I want to use several platforms to do this, and maybe I'm going to get some sort of speed up by splitting the streams, dividing them up on, say, a Haskell evaluator on my CPU, some CUDA-capable GPU, and an FPGA or whatever, and do the result, do some data parallel computation, bring them all back together again. That's not what I'm going to talk about, how you do that. That's, what I want is maybe I write a program like this in Haskell, and there's some combinator run stream which does all the heavy lifting for me. That's not what this talk is about. The talk is about, for me, is about F, the function itself. In particular, I'm concerned with how can I statically verify that my heterogeneous program is going to do what I say it does. So, for example, can I statically check whether or not the program F is well typed on the platforms I wish to run it on? So, I've got a Haskell platform which supports, various crazy type system extensions, higher order functions, the lot, CUDA, which, well, severely limited in that respect. I don't have higher order functions, recursion, got a fixed set of types, which are generally scalar values. And maybe I've got an FPGA as well, which is the sort of thorn in my side. It only supports one operation, one type. And maybe I write my program like this, so I've got F, which is maybe some little safe division operation. And I say, give me the stream Zs, where, I zip up these streams X and Ys, using Haskell CUDA and the FPGA. And what I want is for the compiler to go, stop right there. There is a type error. The FPGA doesn't support division. And it might not give me an error message that nice, but this talk is about how we can do that. So, DSLs. So I'm going to use an embedded DSL to do this, because I want to write the program F once, and through some operator overloading, for example, generate this syntax tree. So, it's not quite Hutton's razor, but it's the same sort of idea. I've got polymorphic values, conditional expressions, say, and equality. And for those not familiar with Haskell, the EQA constraint up there basically says that A is a type, there's a set, has decidable equality effectively. So EQ is a set of types of decidable equality. And my expression through various operator overloadings, say if Y, then else, desugars down to some tree. And what I want is to be able to compile this tree to various different platforms, if they support it. So, the Haskell backend is pretty straightforward, because Haskell supports all the types, right? It's the host language. So I just define the type-list evaluator, which is burned into many people's retinas by now. Probably appear 3 times more before we leave. Everything's fine here. I just lift values out, as you'd expect. Conditionals, I use Haskell's built-in if-then-else operator. And equality, again, I use the equality method from the EQ type class. But the front end is there. So, let's consider the CUDA backend. So the idea here is that at runtime, I'm going to take my expression and compile it to a piece of CUDA code, and then call the CUDA compiler, say, and link that in dynamically to the run application. So I'm generating a string here, say. And some value comes in, and I want to compile that to CUDA. So presumably I've got this toCUDA function that just says, does the right thing. So if it sees an integer, it compiles, does it x equals blah in some C extension that supports GPUs. But, as I said, the problem is that CUDA doesn't support every possible type, right? So that value Ex could be a massive range of things that aren't going to work on the GPU. So I have to introduce a type class, right? I have to say, okay, what is the class of types that CUDA supports? But now the toCUDA function requires a constraint. So before you can use toCUDA now, you need to know that the type you're compiling is CUDA supported. So you say, no problem, okay, I'm familiar with type class constraints. I'll just stick one on the function. So, piece of cake, right? But that only gets you so far. So you go, the value clause is fine, let's carry on. So now I want to compile an equality expression. You say, well, the way to do that is I compile the two subterms, presumably, they generate a piece of code for each of them, and then I'm going to introduce the equality check. But compiling the subterms requires a CUDA constraint, right? Because we just introduced it. But the problem is you don't know anything about the subterms types, apart from they have a decidable equality. But they don't necessarily have CUDA compatible types. So that's not going to work. And you know, recursion in Haskell especially, and EDSL in general, is such a common thing, it's not a viable technique. So we need something a bit more robust. So you might say, okay, let's go back to the DSL itself. Why don't we just say that if you're going to put value into an expression, you have to prove up front that it's CUDA compatible. And this looks a bit more promising, because now we have that whenever we pattern match on a value, we know by construction that it's compilable to a CUDA backend. But now you've kind of shot yourself in the foot a bit, because let's say you build a value with some lambda in this case. You know, you just build a value, so you say, I've got a value in my hand. You're now sort of duty-bound to compile it to a GPU, because some constraint CUDA pops up, and you say, well, wait a minute, I'm not going to compile it to a GPU. But the type system says, well, too late, you've already committed. You know, you said everything by construction must work on a GPU. And we sort of, in the paper and throughout the talk, I'm going to refer to this as sort of constraint pollution, because, you know, in the worst case, I'm doing this in the context of my FPGA, which supports one type. And you get to the point where, is there any point in making value be polymorphic anymore? You know, we may as well just make it inty, because there's only one type, so now I can only build integer expressions. And I've just severely crippled the range of values that my DSL can be used to express. Of course, this is entirely appropriate if you're only targeting one backend, so accelerate feldspar, for example, though arguably accelerate targets more than one at the moment. But if you just focus on a particular set of types and compiling that type to a range of backends, this is fine. But you know, here we're trying to solve a problem where I've got Haskell and GPU, which are vastly different, and it would be a shame if I had to restrict the set of values that my Haskell evaluator could work with, simply because down the road I may wish to target an FPGA. So, if in doubt, add another layer of abstraction, right? So, let's parameterize expressions by the constraint we wish to introduce. Now, GHC, just about the right time I was doing this work, introduced first class constraints. So we can just say here, C is a constraint, like CUDA, for example. And we can parameterize our type by that. And everything seems to work. So here, any presumably is the class of all types. And CUDA is the class we had before. And we just fix those types in our evaluate and next to CUDA functions. We say evaluate expressions which are constrained by any, and next to CUDA express puts the CUDA constraint before. And things like our lambda work just as before. We just end up with some constraint C over our function type. But it doesn't matter, really, because only at the point where we pick C will we be forced to say, well, do we support functions or not? And this is effectively what John Hughes proposes in restricted data types. But it's still not perfect, unfortunately. So this is great again, until you try to use two things at the same time. So for us, the problem now crops up with the heterogeneity aspect. So in my runStream method, if I specialize it, say, to compile to Haskell and CUDA, there will come a point where I have to simultaneously take the function f, and from that one expression generate two different pieces of code, right? And this corresponds to instantiating C twice. So 1 point for any and 1 point to CUDA. And you can't do that, right? You know, as soon as I unify, it doesn't matter which way I go, I can't unify CUDA and any. So the Haskell programmers in the audience will think, well, when this happens, you just introduce a rank2 type. Perhaps now you've got two problems, but... So now it type checks. So what I've said here is the argument is of type for all C, XCA. So you can pick C as many times as you want, and that's great. But you can't actually produce a value of that type because now you're saying, okay, well this function accepts values that by construction don't rely on the constraint. This, you know, it has to work for any constraint C. So what kind of constraint is that? Well, so, and some people will be happy at this point, really. If the program type checks, it's correct. It doesn't matter whether I run it. But unfortunately, my supervisor won't. So, I will. So, we're back to square one. We've got three sort of solutions, and they work in different situations, but not mine. And that's why these conferences exist, right? So, what are we going to do? Well, really, the first solution, whilst being very limited in the sense that it couldn't handle with this basic recursion, is the right approach. The constraint belongs with the application, right? It belongs with the CUDA compiler. It doesn't belong on the type. But yeah, the recursion doesn't work, which is really, really annoying. And the reason the recursion doesn't work is because the top level type XA doesn't really tell you anything. It's not rich enough to convey all the types that might appear in the tree. So what we're going to do is, we're going to capture that entire set of types. So let's say we've got this equality between two characters. We're not just going to capture the fact that it returns a Boolean, we're also going to capture the fact that it is comparing characters. So we're going to associate each type with some set A's, each expression with some set A's of the types that it talks about. And then we want some kind of constraint that says, well, for every B that appears in these A's, that is a CUDA compatible type, for example. And then we can rewrite the CUDA function to say, we're not going to use toCUDA anymore, we're going to use a new function, toCUDA1of, that says, well, if you've got one of the B's in these A's, it's a CUDA compatible type, so you can use that function. But how do we capture every type in the argument? Well, we do the dirty thing, right? We parameterize expressions by the set A's. And each constructor, it's true we have to go back to the type and constrain it, but we're going to constrain it once, and it's going to work for every backend. And the constraints we're going to introduce are going to be of this form A in A's. And we're going to say, look, so if you build a value, then the type you lift A must now appear in that set A's. And similarly, if you build a conditional or equality test expression, the values you're sort of producing by condition or testing for equality appear, but also Boolean appears, because by nature these consumer produce Booleans. And now, something like this equality is associated by its type with the type's charable, and we can tell just by looking at it exactly what's in it. So now we can just write a constraint that talks about that entire set A's, and not just, you know, the top level type. And we'll call it all CUDA in this instance. And all CUDA is going to provide that toCUDA1of method, which basically says, look, if you have some element A that is in the set, I'll let you trade that for the CUDA instance that you need, right? And I'll give you the function that takes that A and gives you the CUDA code, which is a string. So I guess the question every lips now is, how does all CUDA work, right? So this is my G-fold-L, I suppose. So the interesting case is, well, let's say you've got the set A's, and you've got one more type A that is a CUDA type, and you want to extend it to build this bigger set. Now, I've implemented sets as lists, but conceptually they're sets, so that's why cont appears. So the premise is this: toCUDA1of is going to have to take a value of type B, right? And we don't know what B is; it's completely unknown, but we know that it's in the set, or the list, A cons A's. Right? So that's all we know. We just know it's in the set. So So what does that LM sort of constraint give us? Well, essentially it gives you a piece of evidence that tells you where in that set you should be looking for the instance you need. Right? And what's a piece of evidence? Well, there's only two places something could be in a list, right? It's either at the head, in which case the thing you're looking for unifies directly with the head of the list, or you've got some evidence that it's in the tail and the head is some type you don't care about. And the important thing is that once you've done that, when you pattern match, what you have to do is say, well look, give me the evidence, where's B in the list? And if head comes out by magic, and equality, this introduces this quality constraint, you can say, so B is A, I have the CUDA instance, do it. And in every other case you would guess. And sort of by luck, or by construction, depending on how you look at it, it all just works. And the best thing is we get type inference back, because we don't need a high rank type here to say these things. We can just say, here are the platforms we're using, and the compiler says, oh, well, that needs all CUDA, that needs all them. Better, sets of types, well, they're just that, right? Sets of types. So if you can represent something as a type, you can constrain it in this way. So for example, here we could parameterize expressions by list O's of operations. And then we have the ability to say, well, this expression is used, in this case, values. And this is useful to say on CUDA, where you might want to avoid using conditional expressions because it's a SIMD architecture and it costs you performance to have sort of divergence. You might say, well, if the cond operation appears in this expression, reject it statically, don't compile it. And yeah, so it turns out to be a more general issue. So some conclusions. Well, effectively all I've done is show you how to separate interface from implementation. And perhaps this is folklore, but it took us a while to come up with this. And we get type inference and operator overloading back, which is key. So the user doesn't have to deal with this. They just write their program, using all the lovely syntax that Haskell offers, and the types just pop out. And yeah, maybe it's applicable elsewhere, not just constraining types, but operations. Some other stuff in the paper, if you're interested. It does work with tagless representations, so where you use functions instead of data. So there you have to introduce things like high rank types, and it still works. And if you think the all CUDA classes are open, get rid of those as well. The constraints are mechanically derivable in a lot of cases, so no boilerplate. And we can also, if we're constraining operations, it turns out that we can prove the totality of functions using these that omit certain clauses. And of course, these are just data types. DSLs is just one application, so it might work elsewhere. Thanks for listening. Yes?